we have a 30-kilogram child sitting on the outside edge of a 700-kilogram merry-go-round, rotating at 0.5 revolutions per second. Radius of the merry-go-round is 2 meters, and it can be treated as a uniform disc. If the child stands up and walks towards the center, so she or he is now half a meter from the center, what will be the rotation rate of the merry-go-round? So the merry-go-round is rotating initially at half a revolution per second. The kid is originally sitting on the outside edge. Kid gets up, walks in, here's the rotation axis. Kid walks up until he or she is right here, a distance of half a meter from the rotation axis. Angular momentum is conserved in collisions, but it's also conserved in any system where all you're doing is redistributing the mass. This is just a redistribution of the mass. The kid is moving, but the merry-go-round and the kid are the system. So we can say that the initial angular momentum of the system has to equal the final angular momentum of the system. Now the kid's rotating at the same rate as the merry-go-round, because he's on the merry-go-round. He's not running along the edges, he's just standing there. When he walks into the center, he just walks on a straight line towards the center. He doesn't walk parallel to the rotation. So initially, angular momentum depends upon the moment of inertia. So we need I for the merry-go-round plus I for the kid. You cannot add the mass of the kid to the mass of the merry-go-round and then treat it all as a cylinder. If you did, what does that imply? The kid is spread uniformly over the cylinder. Okay, this kid is not smeared out uniformly over the whole cylinder. Kid's sitting in one spot. So we can simply add their moments of inertia. That's not a problem. But we have to add their moments of inertia and not their masses. The equation looks the same. What's changing is the moment of inertia of the kid. That's changing from beginning to end. The moment of inertia of the merry-go-round is not changing. Merry-go-round has a set mass, it has a set radius, it has a set moment of inertia. Okay? Now, typically, in our equation here for angular momentum, omega, if you are solving for angular momentum specifically, omega needs to be in radians per second, okay, in order for the units to work properly. If you're relating initial angular momentum to final angular momentum, you can use whatever units you want for omega, and that's the units you'll get for the final omega. Okay? So if you're using this equation to actually solve for angular momentum overall, you have to be in radians per second for omega. But if you're relating the two, you can be in whatever units you want. So I of the merry-go-round. I of the merry-go-round will be 1/2 mass of the merry-go-round. I made it awfully big. Sorry. It's okay. So the moment of inertia, we're told that it can be treated as a uniform cylinder or disc. So 1/2 mr squared off the table. How do we find the moment of inertia of the kid?
mr squared.
Mr squared. The kid can be treated as a point mass. He's awfully small compared to the 2 meters from the rotation axis. So plus the mass of the kid times the radius. So the radius he's sitting initially is 2 meters. So there's our initial angular momentum. The initial angular velocity is 1/2 a revolution per second. finally, that has to equal moment of inertia again. The thing that changes here is the radius. The kid is now half a meter from the rotation axis. Now, even though there's an eye of the merry-go-round on both sides, and it's the same on both sides, we can't cancel it out. That would be so nice if we could, but we can't. And that's because we're multiplied by omega. The omegas would have to be the same as well. So let's plug and chug here to find omega final. Let me know if you agree. I'm a little challenged when it comes to using this calculator. Because we had this initial angular velocity in revolutions per second, that's giving us our final angular velocity in revolutions per second. Spinning faster. Does that make sense that it's spinning faster? Since he moved towards the center, that put the mass closer to the rotation axis, so that decreased the moment of inertia. Moment of inertia is smaller, so that makes omega get bigger in accordance. Questions? Are you getting different numbers than I did? Did I plug it in wrong? 1.07 is what I got. So for those of you getting different numbers, what are you getting? 0.54. Other people agreeing with that? Okay. So for this term, I get 1401.2. The units will be kilogram meter squared. Times that by 0.5. This whole side I get 700.6. So this side 0.5 times 700 is 2 squared. 1407.5. So that doesn't make any sense at all. 14. It's not my battery that's dead. The power button doesn't work. Multiple times. Sit there, hit it. Okay, now I'm getting 1520 for this. So 760 over here. So So this is probably wrong too. Let me try that again. 0.5 times 700. I get the same number here.
Yeah, that number's right.
Yeah, so 0.54. I'm not sure what the mistake was, but there's certainly a mistake somewhere.
Multiplying the 0.5 in voltmeters revolutions per second.
That certainly could be it. Definitely. Thank you. Okay, sorry about that. So it's 0.54 revolutions per second. That makes more sense to me. Because a merry-go-round being 700 kilograms and a 30-kilogram kid, it shouldn't seem like it would make as big of a difference.